And before we move on, I just want to recap exactly where we finished off in the lecture on Wednesday. So we were looking at complex power series, yeah? In particular, we were looking at the exponential function, sine function, cos function. And basically, we extended the real cases of those functions to the complex case. And we saw that the complex extension, or complex extensions are continuous, but some of the other properties are different, okay? And we finished off by looking at the exponential function, and we saw that the exponential function in terms of complex numbers is 2 pi I periodic, okay? But if you think of the real case, the exponential function is not periodic. Right, so today then, I want to go back to sine and cos, yeah, in terms of complex numbers. And we will look at some further properties of these functions. Right, well, first of all, we have the following representations. So if we look at I sine z, then this has series expansion, sum from 0 to infinity, iz to the 2k plus 1 over 2k plus 1 factorial, and cos z is the sum from 0 to infinity, iz to the 2k over 2k factorial. Okay, we've seen this before. Right. Well, this implies that we have the following two equations. So we have cos z plus I sine z is equal to the exponential of iz. So basically, if you sum these two series, you will see that you've got the series of the exponential of iz, yeah? Another series that we've looked at previously, okay? And we also get that cos z minus I sine z is the exponential of minus I z, okay? Similar calculation. Right, I will label these equations because I'm going to use them. So basically, we've got simultaneous equations, and we will solve them as follows. So if we subtract equation 2 from equation 1 and divide by 2i, we get an expression for sine z in terms of the exponential function. Right, so this gives the following. So we get sine z is the exponential of iz minus the exponential of minus iz over 2i. So this is what I just mentioned. So if we take equation 1, subtract equation 2, and divide by 2i, yeah? And then similarly then for cos z, we get the exponential of iz plus the exponential of minus iz over 2, okay? And this comes from taking the sum of the two previous equations and just dividing by 2, okay? You'll see by doing these operations on the previous equations, we get expressions for sine z and cos z in terms of the exponential, okay? Right. What we will do next is we will consider z to be a purely imaginary complex number. So it'll have a 0 real part. Right, so now for z to be equal to just iy, yeah, a purely imaginary complex number, we will write down what we have for each, for sine z and cos z in this case. Yeah. So we get that sine, well, it'll now be iy, yeah, will be e to the minus y. Okay, I'm changing notation, but you know what I mean. Minus e to the y over 2i from this equation. Yeah. And then for the second, we get cos iy. And this is e to the minus y plus e to the y. This is over 2. Okay. Again, doing the same thing, but for this second expression for cos z. So basically, just substitute x. If you just write z as x plus iy and let x to be equal to 0. Okay. Well, this implies that the modulus of sine iy and the modulus of cos iy are unbounded. If you look at the modulus of each of these expressions, you will see that they're unbounded. Okay? This implies that cos and sine, in terms of complex numbers, are unbounded. If you think of the way we consider boundedness in the complex numbers, what we do is basically look at the modulus. Yeah, we did this earlier in the course. Okay. However, in terms of the real numbers, everyone's familiar with sine and cos in terms of the real numbers. These are bounded functions, yeah? But in the complex case, they're not. Okay? This is another example of, okay, we've got continuous extensions of these functions to the complex case, but the properties may differ. Yeah? Right. However, on R, they are not, obviously.